to freeze. There we go. So you didn't get to watch the video. What's that?
It's just nothing but bangers out there. It's crazy.
So to fuck around as human, to find out as divine.
You're quite the philosopher back there. All right, so we had left off talking about theories of magnetism. And I said it is B. And now that you're back, we can finish this. And I said, we're done. So it be like this. It is believed. Probably didn't know I was going with that one. Believed that atoms have we already talked about this, so last video. And we ended up talking about the domain theory, and so now I'm just going to make some notes about that. So it is believed that atoms have a magnetic field. When electrons orbit randomly, the fields cancel each other out. Period. But when a part is exposed to a magnetic field, the atoms, or I should say electrons, the thing I copied off and read this in, it actually said the atoms, and then it said electrons, like that, align and the part becomes magnetized. A-L-I-G-N, align, and the part becomes magnetized. And then we talked about my more favorite theory, which was the domain theory. So the domain theory, you remember what a domain is? It's just all these little things right there. Each one of those is a domain according to this theory. Every one of the little magnets is a domain. The domain theory is that a part contains little magnets. Called domains. When a part is magnetized, the domains align, and the part becomes magnetized. Pause for effect. Yeah. Well, how do we unmagnetize or demagnetize? Put it in a machine. What does a machine do? It scrambles it. So the machine can either line it up or it can scramble it. So we'll talk more about demagnetizing later, but what I'm doing when I put your rotor in the machine, and by the way, we don't do that in the field with rotors because that would not be something we do. Why would we demagnetize a magnetorotor? We're only doing it here for fun, because it's fun. And then you can see how much magnetism you can put back in it. So it's just for fun, just a teaching thing. But to demagnetize it, we put it in the machine, and it uses alternating current, which goes back and forth and diminishes. So it scrambles those domains and leaves them all over the place again. And so once they're scrambled, then you don't have the magnetism left in the part anymore. And then you're going to take it, you're going to put it into a machine, and you're going to put DC current through it. And DC current only goes one way, and it will magnetize the part back to normal. Now, interestingly enough, what would happen if I used AC current?
Nothing. You get high.
Actually, AC current magnetizes quite well. It's very shocking. I know, but it has what's called a skin effect. And so when we use AC current to magnetize something, and I don't really understand why it does this, but it's like the magnetism rises to the surface, and it causes magnetism to go across the surface instead of deep down inside of it. So DC magnetism puts it way deep inside. Actually, it won't show as well on the outside as it will with AC. AC will give you a much better indicator on, if we use one of those little Gauss meters that you guys are using, it's called a Gauss meter that checks the magnetism. You would get a higher reading if we used AC because it's more on the outside than on the inside. So, all right, let's talk about some magnetism terms here. Residual magnetism. Well, that's just like the name sounds. It's what's left over. So it's the magnetism left in a part after the magnetizing force is removed. It is the magnetism left in a part after the magnetizing force is removed. Some things are only magnetized or magnetic while the magnetizing force is attached to it. So I could take, soft iron. So if we took soft iron over to the Magnaflux machine and I introduced a current through it, and while I'm putting the current through there, I had the Gauss meter next to it, you would see that that part is in fact magnetized. Then as soon as the magnetizing force is removed, you would have very little left. And so that would have very low residual magnetism. So given that, what do you suppose this has? Be a high residual because the magnetizing force. Well, what about this? Oh, look, see, it sticks. Yeah, very low. It sticks. Oh, it did right there. Anyway, it's supposed to be stainless. No, it's not stainless. But yeah, if that would have worked out, that'd been really cool. Then we took it off, and then there's no magnetism whatsoever. So it does work this way, doesn't it? There. Now it's magnetized, right? Mm-hmm. But it's have high or low retentivity.
None.
So very low. None. No magnetic retentivity whatsoever. No residual magnetism. Retentivity is another way of putting it. So soft iron is easily magnetized. So it takes the lines of flux very easily through it. Very happy to be magnetized, but has low residual. Magnetism. Also called retentivity. So low retentivity. Can I move this?
Yep.
No? All right. Strong steel, not mild steel, very strong steel. Also, a more appropriate name would be carbon steel. Carbon steel. You can identify some things. I mean, what would be mild steel? Of course, I'm always thinking about engines. Is kind of the way I go with things. But what are some mild steel? You guys are a big help.
32?
Huh?
032?
032, which is?
Stainless steel?
It's aluminum.
It's aluminum.
Yeah, 032. Oh, sorry, 032 is the thickness. Sorry, I'm
We'll
thinking.
say-
Huh?
We'll say.
Oh,
Safety wires.
Safety wire. That's stainless steel, yeah. Well, if we're talking about engine stuff inside of the engine, connecting rods are not carbon steel. It's things that'll bend before it cracks and breaks. So connecting rods are something you want to bend before it would snap off and break. A lot of times gears, but not the actual teeth. Gears can be more of a mild steel, but the gears then are not. They're hardened.
what are power pins made of?
What's that?
Power pins?
Mild steel,
Yeah.
definitely, because you got to bend them.
Yeah.
Cotter pins. Not so much bolts, but things like a crankshaft. Crankshaft, you want it really strong, so that's going to have a lot of carbon to it. So strong steel, anything that's got a lot of carbon that's very strong, is much more difficult to magnetize. Takes a lot more current. Much more difficult to magnetize, but once you get it there, it tends to want to stay, but has a much higher residual magnetism, has a much higher residual magnetism, which would be high retentivity. High retentivity. Let's see, permeability. Permeability, it's the ability of a metal to become magnetized. The ability of a metal to become magnetized. So soft iron, that have high or low retentivity? Low, okay. It has high permeability, which means it's easily magnetized. But low retentivity. And carbon steel would have,
Low permeability.
so carbon steel would have low permeability. It's not so happy to be magnetized, but it has high retentivity. Once you get it there, it's there. This becomes an important point when we get into non-destructive testing with magnetic particle. And the reason why is because you have to identify the metal that you're working with, which dictates the method of which you're going to add the particles to look for discontinuities. In soft iron, you actually have to apply the media that looks for the discontinuities while the magnetizing force is actually on the part, because it has such a low retentivity. When you take away the magnetizing force, if you put these iron filings in there, it would be attracted to a crack, but as soon as you turn off the machine, there's no more flux leakage and the filings would just fall right off. So you have to actually magnetize it. You have to have the current running while you put the stuff on, and then you can look at it. It'll stick at that point unless you start messing with it. Carbon steel, you can actually put the current on, then apply the stuff. And you can wipe it off and apply it again, and wipe it off, apply it again, because it's just going to be that way until you get rid of the magnetism. And last term here is reluctance. Reluctance. The opposition of a material to magnetic lines of flux. It's like resistance. The opposition of a material to magnetic lines of flux. Yeah, I would think a reluctance is more like an insulator, like a flux insulator. All right, the reason why I tell you about all this magnet stuff is because we're going to talk about how a magneto works, which depends on magnets. There's times when you want something magnetized, something when you don't. But before we get into the magnetos and exactly how they work in more nuance, we're going to put a pin in that, as my wife would say, and we're going to talk about ignition systems. But we're going to back up a little bit and start with an older style. I don't know if it'd be older than, probably Magneto's older. My father-in-law had a 24 Dodge. It had a magneto. So magnetos are probably first, but it's easier to understand a battery ignition system and then move on to that because a battery system has fewer moving parts. So talking about that, we're going to talk about the Kettering ignition. Kettering ignition, also known as a battery ignition system. So also known as a battery ignition system. We're talking about old school battery, not this stuff you have in your cars nowadays. It's all digital and electronic. I would just simply draw a box and then a spark plug and a battery and say, well, you got a battery, goes to a box goes to a spark plug, and you're done. So there you go. There's your modern day ignition systems. But the old-timey Kettering is a little bit different. So I don't think I've ever really seen this in an airplane. Might have. I had a friend who had a Volksplane. And might have done that. So this is used on older cars, boats, some aircraft, possibly home built. I don't know. All right, principle of operation. Principle of operation. We're going to put together some of the stuff that we've already learned and just see how it all works, because there's not a lot that's new in what we're going to look at, just the way it works. Well, why do we need an ignition system anyway? Got to have a spark, and the spark ignites the fuel-air mixture in the cylinder. Don't say in the head. It's called cylinder. And the ignition in aircraft is so old and so antiquated, but it works, and it's reliable up until the point when it's not. In your car, you know, even going back to my father-in-law's 1924 Dodge Brothers sedan, the timing wasn't set. You could advance the timing, retard the timing. What I mean by that is, I should have pulled up my little video here, but
It's a lot of controls.
what's that?
It's a lot of controls.
In the car?
Yeah.
Yeah, it does. It's on the steering wheel, spark advance, and you had to get it just right. So in our cars, the computer controls exactly where the spark is going to go. So You guys haven't had engines yet, but one second. Slow that down. There we go. All right. So this is a 4-stroke engine. There are 4 strokes that are going to happen, 5 events. 4 strokes, 5 events. And the strokes are, we'll get it in order here. Ready, set, go. Intake. Intake stroke is from the top to the bottom. So the piston starts at the top, it draws a suction. And during that time, there's a way I can, there we go, I backed it up right there. So the piston is coming down, the intake valve is open, and it draws in like a syringe fuel and air mixture. And when it gets down to the bottom of that, this is actually kind of a simplified version of how an engine really works. They're a little more complicated, and then the timing is different. When it gets down to the bottom, then you're going to see that valve close, bang, intake valve closed, and the piston is going to go up, and it's going to squeeze all that, and then this one's going to, right there at the very tippy top, the spark plug fires. That is not the way an engine really works. It would be when you're starting, but that spark plug is actually going to go about 25 for us, 24, 25 degrees before top to center. But what I'm talking about is degrees right here, the crankshaft. You can see it's not all the way up yet. It's still got 25 degrees to go before it's going to get to the top. That's where the spark plug fires. And the inertia of the crankshaft and the pistons and all that weight is going to carry this up. So the spark plug fires right there, and the fuel and air starts to burn. It does not explode. If it explodes, that's called a detonation, and it actually can destroy an engine and eat through a piston in seconds. Detonation is really bad. You want a slow, even, controlled burn. So it starts to fuel, it burns out slowly. Well, it starts to burn right there, but things are going so fast that it's still burning, and this piston gets up to the top, right? It creates all this pressure, and burning is already happening, and then that pushes the piston down. There's the burning, right? Gets to the bottom, and then once it's at the bottom, it pushes out all the nasty burnt fuel and air out the exhaust, and then we start the process all over again. All right, so intake, compression, and then we have the ignition. This ignition happens late. Now, the nice thing about this is when you're starting an engine, that's what it's got to look like. You have to fire it at top dead center, because if I fired it, oops, piston's coming up. If I fired it right there, the piston's coming up under the starter, bam, it'll push it right back the other way, and it'll blow teeth out. The starter teeth will go out, and Continentals, they have a big spring inside of the engine that winds up around a drum. It'll launch that spring into the inside of the engine. The only way to get it out is to take the whole engine apart and overhaul it. So you need, for starting purposes, you must have the spark right there. That is called top dead center. And the reason why it's top dead center is, look at how that connecting rod, this is the connecting rod right here. Look how that connecting rod is 100% perfectly in line. Everything is this super straight line all the way up and down. That means it's top dead center. If you're even so much as a little tiny bit either way of that, you are no longer on top dead center. Even though the piston, if this was an accurate, I mean, they can only put so many frames in there, the piston actually goes to the top and pretty much stops, and then that connecting rod kind of sweeps through and then down. So top dead center, what's that called? Bottom dead center. All right, so we got that? All right, just a little refresher there. All right, so back to what I was thinking about. All right, so principle of operation. So we got to create this spark, and it's got to be done at the right time. In your car, as I was saying, where that ignition event happens, it's all over the place. You got a computer thinking about what's going on. It's measuring your manifold pressure. It's got a knock sensor looking for detonation and pinging. It's got the computer control for the fuel. It's got everything going on. It's thinking about it. Now we're going to go a little bit advanced, a little retarded. Oh, he wants to go fast. We're going to advance the spark plug. In aircraft, you got this thing. It's got 2 flavors. right where you put it, and if you got an impulse and it has a retard on it, which will retard it X number of degrees depending on the part that the impulse you put on. But for the most part, we look at the engine, and the engine manufacturer will tell you this engine should fire at 24 degrees before top dead center. Well, then you put the engine on 24 degrees top dead center. You put this on perfectly at 24 degrees top dead center, and that's where it's supposed to fire for its whole life, 24 degrees top dead center. It doesn't know advance. It doesn't know retard. It just, boop, that's it. That's what you do. So, but backing up again, talking about the Kettering ignition system, the drawback to this system and why we can't use this on airplanes is because of the first component. Battery. Why don't we want battery ignition in an airplane?
Because if the battery fails and you don't have an ignition system.
Boom, battery fails, you don't have an ignition system. Well, again, you guys are right here at this precipice is the word I want, where we're going from old analog non-technology. This hasn't evolved in, well, this is an old lunchbox. This is the OG Bendix. This is a Bendix lunchbox magneto. It's called lunchbox because, like my grandpa had a lunchbox that looked like this. They called it a lunchbox. So this is pretty much one of the original Bendix magnetos. And it's got a rotating magnet and a rotating drum in there and a coil and points. And it's got the exact same thing as this. You should see what a modern day brand new Bendix magneto looks like. It looks exactly like this, just shiny black. All right, that's just, here's a modern day slick magneto. I just bought some. You know what it looked like? Exactly like that without the scratches on it. That's it. No difference. Everything's the same. Technology is just, once they went from that to those, they were done. All right, that's good. Call it a day. Just keep doing it. Well, yeah. I'll tell you stories about them doing that and then breaking it. And I'm like, ooh, yeah. All right, so we can't have a battery, but where I was going with that is, guess what we have now? So when I just replaced the magnetos on my airplane, because you want to do a 500-hour, or if you have a Bendix, you want to do a 500-hour inspection on them every 500, you want to. If you have a slick, you really should throw them away every 500 hours. And given that I was taking my airplane across the country twice, I thought, yeah, I don't need a magneto problem, in Kansas somewhere. So I hit 500 hours, put on some brand new overhauled ones. But one of the choices that I had now is they have electronic ignitions. So there is a supplemental type certificate, which means the FAA will allow you to do it, because the type certificate for my airplane and engine say, that's the magneto you will have, right? But somebody's making these electronic ones now, no moving parts. It's all electronic. You just put it on the back, and it's going to have a part that spins just like a magneto, just so it can sense where things are. And you have that, right? The Surefly? Did you? Okay, one though. Yes. And you take off one magneto, throw it away, put it on the Surefly. Well, how long is that good for? Until you overhaul the engine. I mean, the thing's good for like 2,000 hours, no moving parts. Drawback, it needs a battery, right? It needs a battery. Okay, thanks. He's going to lock the door for me. So now we have this new technology. In fact, we were just talking about the other day, I didn't realize that they make an STC for at least your airplane where you can throw it all off and put two Surefly or electronic ignition. Different company, okay. So there's different companies. But you can now put two electronic ignitions, but
You have to have a redundant battery.
need a second battery.
And
But
wiring.
in your airplane, you still have an electronic and an analog?
No, he does, yes.
Yeah, I see.
Right now.
One, Slick probably, or I don't know, Bendix or a Slick, and then the other one. There's one drawback that I may be going, yeah. That one has, depending on how you set it up, has Spark Advance built into it. But our engines they're designed for two spark plugs. So all aircraft engines, if they're an aircraft engine, have two spark plugs and two magnetos. Because
Redundancy is nice.
redundancy is nice. Yeah, if you lose one magneto, I'd rather not just crash. Oh, should have had two. So they have to have two magnetos. Well, if you're going to have dual ignition system, somebody figured out, let's take advantage of this. let's think about how to set this engine up. So like Continentals have one spark plug goes in straight and one goes in crooked and points towards the exhaust valve. So it aims it a different way. Some Continentals have staggered timing. One fires at 24, one fires at 28, different times, but the same cylinder. And the reason why they do that is they want that flame front where it starts burning to burn evenly across the cylinder. Well, inside of a cylinder, the air mixture is not the same everywhere. One side they found out is a little richer than the other side. A rich mixture is going to burn at a different speed than a lean mixture. So they figured this out and said, okay, since we're going to use 2 spark plugs, this is how we want to do things so that it burns, starts this great flame front and burns perfectly across, and that's the way it should run. And if you shut off either one of those spark plugs, your exhaust gas temperature instantly starts rising. I mean, it doesn't keep rising, it's just woo! I mean, it's just a big jump in exhaust gas temperature. When if your exhaust gas temperature goes up, that's somewhat of an indication that you have an impartial burn and it's burning later. So less efficient. You're losing heat out of the exhaust pipe, and it's a heat engine, so if you're losing that. So anyway, so I'm thinking about that, and in order to utilize the Spark Advance, you turn off one of your magnetos, which there goes your efficiency. But they claim that it's more efficient and more powerful. So I don't know. You do with that with what you want. I think the best of both worlds would be if they had somehow could take that electronic ignition and fire all the plugs with a magneto backup. I don't know. Probably just the battery backup's the way to go. But moving on to this, we're talking about the battery ignition system. We've got a battery. We've got a switch. And we're going to run it through a transformer, which means we're going to have a coil. And we're going to run that coil over to, I'll draw it over here, a set of points. Points are nothing more than a switch. Call them breaker points, points. It's just these little guys right here. It's got a piece of spring steel on it, so it's a switch, and they're held closed together. So they're always held closed by their normal pressure. And then there's some sort of camshaft, and we usually just draw a camshaft as a little square because it's easy to do. So when it's on the flat spot, obviously it'll allow the points to come closed, and then as the cam opens up, it'll move that. And that cam is going to be attached, that's a cam, or the breaker cam, if you will. It's the cam inside of the magneto. It's not the cam that drives the valves. This right here is a camshaft, this orange piece right here. And I always say the crankshaft, that's this red one right here, the crankshaft is the brute part, that's the muscles of the engine, but the camshaft is the brains of the engine. And the reason why is because the crankshaft, all it knows is up, down. Yeah.
What's a cam?
I'm going to get to that. So I'm glad you asked. So the crankshaft, everybody got what a crankshaft is? Crankshaft is the muscles of the engine. It knows up and down. So it goes up and down. It turns reciprocating, means up and down motion, into rotary motion. So here it is. It's just kind of, there's the power stroke, and that's what made this go. And now it's just inertia keeping it going. Usually there's a flyweight if it's a single piston, or if it's, more pistons, they're doing something else right now to keep the whole thing going. But this orange piece over here, the camshaft, has to be the brains of the operation. This is not drawn correctly. Right now you see it, you can maybe hit the lights real so you can see the colors on this. You can see that it's got a lobe on it, so this is the cam. The cam is the thing that has to open and close the valves. In this application, to make it right, they would have to draw it in another way, because you have to have something, the same mechanism, a rocker arm over here riding on a cam. So we could have put dual cams on here. Engines, some have dual cams. But you can see that this has to know when to open that exhaust valve. And it only opens that exhaust valve every other rotation. So the crankshaft is spinning twice as fast as the camshaft. And in a normal camshaft, I shouldn't say normal, like an aircraft camshaft, older anything that doesn't have an overhead cam, actually overhead cam, maybe too. Most cam shafts are about as long as the engine is, and they're going to have lobes for the lobes for every single valve on there, and so that camshaft has to know, when do I open the intake? When do I close the intake? When do I open the exhaust? When do I close the exhaust? So it's thinking about this all the time. And you've got to have that time just right. And you can imagine if you just threw this together and the teeth were open and one of the valves opened right here, you'd have a big problem. Right? So it's all got to be timed. That's your engine timing right there. So because the camshaft is the brains of the operation, and it has to know when the valves close, when the valves open, you can run this cam that I have here, this little cam that's the breaker cam. You would run that off of the camshaft because it's the brains of the operation. So it usually runs off of that in this ignition system. So like your car, it's so hard because cars are so new and modern now, but your older cars, your lawnmower has a magneto.
It does.
So your old, like my boat, my old Mastercraft, it's got a distributor that sits there with the spark plug wires coming out of it, and that actually has a shaft that goes down, and it's running off of a gear that's running off of the camshaft, and so that's how all that works. All right, so we've got a transformer. Transformer's going to have what here? What's that in the middle? A soft iron core. Okay. And we're going to have I'm going to miss some things here. We also want to put something over here. There we go. All right. You know what? Let's do this here. I'm going to take this out of the equation here for a reason. So if I look at this right now, and I pulled out my core back out, I could say what I've drawn right here in this ignition system is what I would call the primary circuit. Now, a magneto is going to have three circuits. It's going to have the magnetic, the primary, the secondary. We don't have a magnet running around here. We're using a battery to supply power. So I've got, I'm just going to call that the primary circuit right there. And I guess if we had to, draw something in there that was magnetic, I would say, well, the only thing in the magnetic circuit, which we don't really consider, would be the soft iron core, but it's just part of the transformer system. Then we have the secondary circuit, which would have many windings, way more windings, because we're going to do a huge step-up transformer. We'll ground that over here, and that's going to run around over to here, and let's see, we'll make that go there. We'll just make it a 4-cylinder. 1, 2, 3, 4. Put some spark plugs on here. All right, so the blue would be my secondary circuit. So you have a primary and the secondary. And the way this works is we have a switch, which is open, which means it is in the OFF position. So when we close the switch, battery current is going to run through here, go through a coil, energize the coil. And what happens when we energize the coil? I use blue. Blue's always my color to put EMF, so I have to use red. So we get, I don't want to draw on it. So we get this buildup of a magnetic field that happened on the primary, right? Primary magnetic field. Now keep in mind that the way I've drawn it, I've drawn the primary, then a core, and then the secondary. But that's not the way it works. If you looked at it, like I showed you with the, I don't know, Elijah took my stuff. No, that's for a battery.
I think it's across
across the way. Well, that's all right. If we actually looked at a cross section of the area of it, we would see, oh yeah, so I'm going to draw it because I'm really good. All right, so we have the soft iron core, and then we're going to have, it's just not going to do it. We have the primary wrapped around that, and then we'd have the secondary, which would have way more windings. I mean, just all kinds of them wrapped around the outside of that. So you have one wrapped around the other, wrapped around a core. Yeah, because, you know, once you see that drawing right there, be like, oh, well, yeah, there you go. That was terrible, sorry. All right, so we've got them wrapped around there. So again, we've closed the switch. And if the points are closed, here, we'll make them closed. There we go, closed. We're going to have current flow through the primary. We're going to get a buildup of magnetic lines of flux because the primary is a coil, and that's going to build up magnetic field around the primary, which cuts through the secondary. But it didn't happen very fast. It took a little while. How long did it take? I did teach you guys something. So that wasn't a real rapid thing. It's just kind of, you know, built up, and I sighed a little bit. I suppose it did. Get a little of excitement going across there. That's what you'd call it, or induction. But didn't amount to a whole bunch of anything, really. But we've now got current flowing through there, and yeah, whoopee. Nothing's going to happen until the cam starts going around and it starts making these breaker points open and close. So what that does, instead of, you know, because with the magneto we talked about, you have AC, which we'll talk about even more, right? It goes up, it goes down, it goes up, it goes down. Well, the battery doesn't go up and down. It just goes on, it goes off. So we take the points and we open and close it, and now what we're doing with the current going through this primary, on, off, on, off, on, off, on, off, right? And so we'd call that chop DC. So it would kind of be like on, off, on, off, on, off. And when you do that, every time, of course, you go on, you're moving across that secondary coil. Every time you turn it off, bam, snapping shut. And the way we're going to snap it shut is we're going to use a capacitor here. And so when those breaker points start to open, the capacitor, or condenser as it's called in these systems, same thing, is going to do a couple of things. And as I explained before, one, the electrons see that as an easier path. So as the breaker points start to open, electrons pretty much would want to jump across the points, which is going to do a couple of things. One, if you start opening the points, but there's so much voltage across there that it keeps arcing across the points, then it's like they're still closed, they're still closed, they're still closed. Oh, now they'll open. You know, they got to get pretty far apart before it's just open. It's like, well, now how do I determine that? And that becomes very difficult to time it and say, well, if they start opening here, the electrons will finally think it's open by the time it gets here. And that's no way to do anything, because you want it to be at the exact time, because it's got to fire the cylinder at an exact time. So put the capacitor in there. So as the points start to open and electrons would want to jump across that, they'll see a much easier path to go fill up the capacitor, and boom, they'll go fill up the capacitor. And then it'll discharge the capacitor as the points close later. And the other thing is, the points would not last. If it was constantly arcing across, it's going to arc them to pieces, and so you have to change them often. In fact, if you are changing points often in an old car like this, then it's because your capacitor is going out. So, all right, we've got the chopped DC going now. And so when we have the primary expands, whoop, points open, sudden and rapid collapse of the primary, which had the lines of flux going across the secondary. We have flux movement across thousands of windings. We get high voltage, 18, 20, 20. What are you guys laughing about back there? Am I amusing you?
No.
What?
Yes, sure, no.
Yeah, he said, wait a minute.
Share.
It's not really.
Well, now there's all this anticipation.
He's just twisting his mustache up into a handlebar, man.
You're right, it was nothing. If I was a better actor, I kind of would have went with the, what's that, Casino? Is it Casino? With Joe Pesci's like,
Oh, no, it's
The
good.
Goodfellas? Yeah, I love that show. Do you know that one?
Show.
I amuse you? You think I'm over? He's like, never mind. I'll practice it. All right. It involves some foul language. So really, that's it in a nutshell. And so when the point's open and we get that rapid collapse across the secondary, we're going to get somewhere in the neighborhood of 20,000 volts. And that is going to travel up through here to a finger. And that finger is going to be attached again to the cam, which is attached to the cam shaft, which is thinking about where everything's going. And that is going to move around. And when it's right here, it's going to fire this plug, and then it's against the next one to fire that plug, and this one to fire that plug. And so that moves around and fires the plugs in the appropriate way. Assuming you hooked it up correctly, because this happens. People screw this up a lot. A lot. I would say it's probably the number one thing people screw up is getting where the lead goes to the correct cylinder. If this were an aircraft engine, we have 4-cylinder, it would fire 1, then it fires the cylinder 3, then it goes to 2, then it goes to 4. But this, of course, is, if this was a left hand, it'd be this is the first one, this is the second, that's the third, that's the fourth one to fire. So 1 goes to 1, 2 goes to... I didn't draw that right. I'm sorry. See, I told you it's easy to screw up.
So you just need the 2 to go to 3.
Yeah, I know. So 1 goes to cylinder 1. 2 goes to 3. 3 goes to 2. And 4 goes to 4. There we go. See how it's easy, but it's hard.
Why does it do it like that?
Okay, so this is the magnetos are actually labeled which one fires number 1. And so the first one to fire goes to cylinder number 1. The very next one to fire, because the firing order is 1, 3, 2, 4. So it fires cylinder 1, then number 3 fires, then number 2 fires, and number 4 fires. But the next one to fire, we call this is the second one to fire of the magneto. Second one of the magneto needs to go to 3. So that goes to 3. The third one, this is the third one to fire in the magneto, but it must go to cylinder 2. And the last one to fire 4 also goes to 4. So this is the cylinder numbers, and these are the magneto numbers. It goes 1, 2, 3, 4, because that's how it fires. First, second, third, fourth thing to fire. First thing to fire goes to cylinder 1. Second thing to fire goes to 3. Third to fire goes to 2. Fourth goes to 4. That's why during the oral, I always ask you, which direction does your magneto rotate? And I'm surprised how few of you know that. That's okay. And then I turn it around and say, well, which way does the distributor go? Because that's this part back here. I say, well, if this is a left-hand rotating magneto, that means it turns to the left when you're looking at it from the drive end. So it turns to the left. Then I turn it around and I say, then which way does this go?
To the left.
It just goes to the left too. Well, if we all looked at it this way and we're turning this to the left, there's another gear in there. So from this perspective, that top gear is going this way. It's going this way. So which way is it going now? So to you, it's to the left. So if this goes to the left, guess what? Turn it around, this also goes to the left. Just magic how that works. And you need to know that, because if this is the first one to fire, what's the second one to fire? To the left, that one, that one, that one. If you don't know that, you're going to put stuff in the wrong spot. Break time, right?
Break.